Long before the Atlantic Ocean existed, you could have walked from New York to London. Not across ice, not across a land bridge, across solid, continuous ground, because the land that would one day become those two cities was part of the same unbroken landmass. Every continent that exists today was joined together into one, surrounded by a single ocean so vast it covered nearly 70% of the entire surface of the planet. Scientists call that lost world Pangea. It covered nearly 57 million square miles. Every mountain range, every desert, every coastline that would one day become a separate continent, compressed into one. A creature could walk from what would one day become Antarctica to what would one day become Siberia without ever needing to cross open water. The center of this landmass lay thousands of miles from the nearest coastline in every direction. Rain barely reached it. The climate in its interior was unlike anything alive on Earth today: brutal, extreme, and almost completely hostile to life. And yet life flourished at its edges until something changed. What happened to Pangea set in motion the most catastrophic event in the history of life on this planet. Not the extinction that ended the dinosaurs, something far worse. An event so total, so complete, that the world on the other side of it was almost unrecognizable from the one that came before. The man who first proved this world had existed built his entire case from coastlines, fossils, and rocks. The scientific establishment called his idea fantasy. They dismissed him for decades. Then technology caught up and confirmed nearly everything he had argued. The continents beneath our feet are still moving. The cycle that built Pangea never stopped, and the next chapter has already begun. The Atlantic is growing wider. Australia is drifting north. Scientists have already projected the formation of the next supercontinent because the cycle that built Pangea never stopped. Every living thing, including us, traces an unbroken line back through the world of Pangea, through its greatest catastrophe, and into the planet we now call home. Before we continue, if you enjoy stories like this, kindly give us a like and subscribe to the channel if you haven't already. Now let's go back to the beginning to understand why Pangea matters so deeply to the history of life. One idea must come first. That immense continent was never a singular accident. It belonged to a pattern that has shaped Earth for an astonishing span of time, repeating with patience beyond ordinary imagination. The landscapes we know today are part of a cycle that began long before animals, forests, or even complex life appeared. The surface of Earth may appear firm and unchanging beneath our feet, yet it is built from enormous pieces that fit together like a cracked shell. Geologists call these pieces tectonic plates. There are roughly 15 major ones, each carrying continents, ocean floors, or both. They rest upon the mantle, a layer of hot rock buried far below the crust. Although this rock is solid, the tremendous heat and pressure deep within the planet allow it to creep at an almost unimaginable pace, flowing much like cold tar over immense spans of time. Heat escaping from Earth's core keeps that motion alive, and the moving mantle gradually pulls the plates above it. Nothing in this system remains fixed forever. Continents travel because the plates beneath them travel. Sometimes neighboring plates drift toward one another until they collide, raising mountains and joining distant lands into one enormous whole. At other times, they stretch apart, opening new oceans between coastlines that once touched. Every movement is measured in inches across a single year, yet those tiny motions accumulate through billions of seasons, rewriting the face of the planet without ever pausing. The story repeats so consistently that scientists describe it as the supercontinent cycle. The oldest widely recognized chapter begins with Kennerland, assembled around 2,700,000,000 years ago. After its eventual separation came Nuna, also known as Columbia, forming roughly 1,500,000,000 years ago. Rodinia followed around 900 million years ago, gathering much of Earth's land into another united mass before breaking apart once more. Much later, around 335 million years ago, Pangea emerged from another sequence of collisions, becoming the latest great supercontinent preserved in the rocks beneath our world. Each of these continents gathered, endured, and dispersed in its own age. Each reshaped coastlines, climates, oceans, and the living communities that depended upon them. Earlier worlds have been deeply altered by time, leaving scattered clues that require careful reconstruction. Pangea stands apart because its traces remain clearer. Fossils align across modern continents, mountain belts continue beneath oceans, and ancient shorelines still reveal the outlines of a forgotten geography. Every bird, mammal, flowering plant, and person living today belongs to an unbroken history that passed through that connected world. Its place in time stretches far beyond ordinary experience. Imagine compressing the entire existence of Pangea into a single day lasting 24 hours. Humanity would arrive only during the final 3 seconds before midnight, an almost invisible instant after countless generations of drifting continents and changing seas. With that foundation settled beneath the story, the scattered fragments begin fitting together. The next step does not begin with a mountain or a fossil bed. It begins with one determined observer whose careful ideas were greeted with laughter instead of belief. Many of the ideas that reshape science begin with an observation so ordinary that it can be overlooked by almost everyone else. Early in the 20th century, one such observation reached the attention of a German meteorologist named Alfred Wegener. His profession focused on weather and climate, not the history of rocks, and that single detail would follow him through every debate that came after. In 1911, Wegener read a scientific paper describing identical fossils from the Permian period discovered on opposite shores of the Atlantic Ocean. The accepted explanation claimed that vanished land bridges had once stretched across the sea before sinking forever beneath the water. The proposal had become comfortable through repetition, yet it left many details unresolved. Wegener compared maps with unusual care and found himself drawn toward the coastlines instead of the fossils alone. The eastern edge of South America and the western edge of Africa seemed to belong together, almost like pieces separated from the same surface. He looked beyond the modern beaches and examined the true edges of the continents, where the continental shelves descend into the deeper ocean. Using that boundary, the match became striking. The alignment differed by less than 1 degree when carefully measured, far beyond what chance could reasonably explain. Coastlines that appeared distant in the present seemed to preserve the memory of an earlier union. Those observations encouraged Wegener to gather evidence from many branches of science. Rock formations matched across oceans. Fossils appeared in places where crossing wide saltwater seas would have been impossible for the animals that left them behind. Climatic clues also lined up. Ancient glacial marks crossed continents that today lie beneath warm skies, suggesting those lands had once occupied entirely different positions on Earth. In 1912, he presented these ideas in a book titled The Origin of Continents and Oceans. The response from much of the geological community was severe. American geologist Roland Chamberlain dismissed the proposal with open contempt, describing it as utter rot. The American Association of Petroleum Geologists organized a gathering devoted largely to rejecting the concept. Critics returned again and again to one weakness. Wegener had assembled persuasive observations, yet he could not identify the physical force capable of moving entire continents across the planet. Their criticism exposed a genuine gap, although it reached the wrong conclusion. A missing explanation for motion did not erase the observations themselves. Wegener continued refining his work for the next 18 years, collecting additional evidence while receiving little acceptance from the specialists whose approval mattered most. During a weather expedition across Greenland in 1930, he lost his life at 50 years of age. Months later, the following spring, his body was discovered beneath accumulated snow. The debate he had devoted so much of his career to continued without him, carried forward by evidence that kept accumulating long after his final journey ended. Several decades later, discoveries transformed the discussion. Scientists uncovered the slow circulation of Earth's mantle and recognized the continual creation of new ocean floor along underwater ridges. Those findings supplied the mechanism Wegener had lacked. By 1970, continental drift had become one of the foundations of modern geology, supported by observations from many independent fields. Nearly every clue Wegener assembled proved dependable. His reputation changed only after history had already closed the chapter of his own life, leaving his careful persistence as one of science's most enduring examples of truth, waiting patiently for its proper time. As the decades passed, the missing mechanism finally came into view. Once scientists understood that Earth's surface could move through the slow circulation of the mantle, they returned to Alfred Wegener's evidence with fresh instruments, sharper measurements, and far richer collections of data. Instead of finding weaknesses, they uncovered four separate paths leading toward the same destination. Each belonged to a different scientific discipline, and each arrived independently at the conclusion that the continents had once formed a single connected landmass. The first line of evidence came from geometry. Looking only at modern shorelines produces an imperfect match because waves, rivers, and changing sea levels have reshaped the coasts for millions of years. Researchers instead traced the true outer edges of the continents where the continental shelves descend into the deep ocean. Along that boundary, the eastern margin of South America and the western margin of Africa align with striking precision, differing by less than 1 degree. Extending the same reconstruction to the remaining continents produces an arrangement in which ancient coastlines nest together with extraordinary consistency, revealing a world assembled from pieces that once shared continuous edges. Life itself preserves another record. Fossils appear in patterns that become difficult to explain unless distant continents were formerly united. Mesosaurus was a small, freshwater reptile that spent its life in rivers and lakes. Its remains have been discovered only in South Africa and South America. An animal confined to fresh water could never have crossed the broad Atlantic Ocean. Cynaegnathus, a land-dwelling relative of the earliest mammal ancestors, also appears on those same separated continents. Glossopteris, a seed fern with distinctive leaves, left fossils across Antarctica, South America, Africa, India, and Australia. These matching communities resemble pages from the same biological history, later scattered across different continents by the gradual opening of oceans. The third line of evidence lies within the rocks themselves. When molten stone cools, tiny grains, rich in iron, settle into alignment with Earth's magnetic field before becoming locked in place. Because the planet's magnetic field has reversed direction many times through deep history, newly formed ocean floor records alternating bands of opposite magnetic orientation. These magnetic stripes appear as mirror images on both sides of the underwater mountain chains where fresh crust forms. Matching each stripe to the known sequence of magnetic reversals allows scientists to determine the age of the ocean floor and calculate how rapidly continents drifted apart. The seabed has preserved a continuous geological archive, recording the gradual separation of Pangea with remarkable precision. Mountains provide the fourth witness. The Appalachian Mountains seem to reach the Atlantic coast and come to an abrupt end. Across the ocean, mountain ranges in Scotland, Ireland, and Norway continue with the same rock layers, the same ages, and the same patterns of folding created during ancient collisions. When the continents are restored to their former positions, those separate ranges become one continuous chain, built long before the Atlantic Ocean existed and divided only after the land slowly separated. Geometry, fossils, magnetic records, and mountain belts developed through entirely different branches of science. None depended upon the others for support. Together, they formed a body of evidence so consistent that the outline of Pangea emerged with increasing clarity, replacing doubt with one of the strongest foundations in all of modern geology. Pangea entered existence through persistence instead of speed. Its creation unfolded across roughly 100 million years, with continents advancing toward one another at the pace of growing fingernails. From the perspective of a single lifetime, nothing seemed to happen. Across geological ages, entire oceans disappeared, mountain ranges rose into the sky, and scattered lands gradually became one. The earliest major chapter began around 450 million years ago, when the continental core, known as Laurentia, drifted toward Baltica, the landmass that would later become much of northern Europe. Between them stretched the Tethys Sea, an ocean that had existed for millions of years before its floor began descending into the mantle. As the gap narrowed, sediments were squeezed, folded, and lifted. Around 430 million years ago, the collision closed the ocean and thrust enormous mountains upward. The Caledonian Range reached heights estimated at more than 30,000 feet, surpassing the elevation of modern Mount Everest before countless ages of erosion gradually lowered those peaks. The remnants of that towering system remain scattered across today's landscape. The Scottish Highlands preserve part of its western reaches. Matching rocks extend through Scandinavia, while the Appalachian Mountains of eastern North America preserve another distant fragment. Although oceans now separate these ranges, they once belonged to one uninterrupted chain that stretched across a continent still taking shape. Their shared minerals, structures, and ages remain written into the stone, preserving the memory of their common origin. Farther south, another ocean still separated the northern continents from the immense southern landmass called Gondwana. This body of water, known as the Rheic Ocean, slowly narrowed as Gondwana continued its steady northward journey. Across approximately 50 million years, the distance between the opposing shores steadily vanished. Compression thickened the crust, lifted fresh mountain belts, and welded continents that had once occupied distant positions across the globe. The final collision that sealed the Rheic Ocean produced the Hercynian mountain system. Although time has worn those mountains down, their ancient foundations survive within the landscapes of France, Germany, and the Iberian Peninsula. They no longer dominate the horizon as they once did, yet their rocks continue to reveal the tremendous forces that shaped them hundreds of millions of years ago. Where continents collided, they left behind permanent geological scars known as suture zones. These boundaries mark the precise locations where separate pieces of Earth's crust became one. Geologists trace them through differences in mineral composition, pressure-altered rocks, and long bands of deformation preserved deep within the crust. Those buried seams outline the sequence of assembly with remarkable precision, identifying where Laurentia joined Baltica, where Gondwana united with Laurussia, and where the final connections transformed scattered continents into a single landmass. Around 335 million years ago, the assembly reached completion. Every major continent had become part of one continuous expanse of land. Forests, rivers, deserts, and mountain ranges extended across a connected world without interruption from broad oceans. An animal beginning its journey near what would become the South Pole could continue northward for thousands of miles until reaching lands destined to become the Arctic, never encountering open sea along the way. The collisions had forged more than a supercontinent. They had created an entirely new stage upon which climate, landscapes, and life would interact in ways Earth had never experienced before. The outline of that world was complete, and its character emerged from the shape of the land itself. Maps of the modern world encouraged the eye to think in separate pieces, each continent framed by its own coastline and ocean. Pangea offered a completely different view. Its outline curved across the planet in the shape of a broad crescent, resembling a tilted letter C, with most of its land gathered in the southern half of Earth, while its arms stretched toward both polar regions. It was one connected landscape whose scale is difficult to compare with anything that exists today. Within the open curve of that crescent rested the Tethys Sea, a broad tropical embayment extending across the middle of the supercontinent. Sheltered by surrounding land on several sides, it formed a warm inland marine corridor linking distant coastlines. Shallow waters allowed sunlight to reach the seafloor across immense areas, encouraging thriving communities of marine organisms. Rivers descending from nearby highlands emptied into its margins, delivering nutrients that sustained rich coastal ecosystems. Along these shores, life found conditions that remained favorable through long stretches of geological time. Beyond the Tethys lay a body of water unlike any modern ocean. Panthalassa surrounded the entire supercontinent, covering about 70% of Earth's surface. It exceeded the combined size of today's Pacific and Atlantic Oceans, creating a single, uninterrupted expanse that wrapped around the globe. Its enormous dimensions influenced the movement of seawater in unusual ways. Ocean currents followed broad, uncomplicated paths, with little opportunity for the intricate circulation patterns that characterize modern oceans. Polar water mixed only weakly with tropical water, and large portions of the sea remained isolated from vigorous exchange. The contrast between these two marine worlds shaped much of the planet's environmental character. The enclosed Tethys supported extensive reefs, productive shorelines, and varied habitats. Panthalassa, by comparison, possessed fewer regions where nutrients circulated efficiently. Although life certainly existed throughout its waters, many marine communities depended upon the sheltered margins of the Tethys, where sunlight, warm temperatures, and shallow depths combined to create especially favorable conditions. The greatest surprise waited far from every shoreline. The heart of Pangea lay thousands of miles from the nearest ocean in every direction. Moisture that evaporated from surrounding seas traveled inland with prevailing winds, yet each passing mountain range and each additional mile stripped more water from the atmosphere. By the time those air masses reached the continent's center, little moisture remained. Rain became increasingly uncommon until broad regions received almost none at all. Such immense dryness transformed the interior into an environment unlike the coast. Rivers became scarce, vegetation thinned, and seasonal changes could produce dramatic swings between heat and cold. Without nearby oceans to moderate temperature, the land responded rapidly to changing seasons. Conditions that supported abundant forests along distant margins gradually gave way to landscapes where survival demanded very different adaptations. Evidence for this striking climatic contrast survives within the rocks themselves. Thick layers of wind shaped sandstone preserve the forms of towering dunes that once migrated across immense deserts. Beds of salt and gypsum record places where shallow bodies of water repeatedly evaporated beneath persistent heat, leaving minerals behind as the water disappeared. These formations remain long after the weather that created them has faded. Pangea carried many environments within its single outline, from productive tropical coasts to dry continental interiors. Its geography alone created one of the strongest climate gradients ever recorded on land, leaving an enduring archive written across stone instead of memory. Weather follows familiar rhythms across the modern world because oceans divide the continents into manageable pieces. Pangea erased that balance. With one landmass stretching from polar latitudes across the equator and extending thousands of miles from shore to interior, the atmosphere behaved according to a different set of rules. The continent generated a climate system so distinctive that scientists gave it a name of its own, the Pangean megamonsoon. The driving force behind this immense cycle was a simple property of nature. Land gains heat much more rapidly than water, and it also releases that heat much more quickly. During summer, sunlight poured across the broad interior of Pangea, warming the ground until enormous masses of heated air began to rise. As that air climbed, lower pressure developed over the continent. Moist air from the Tethys Sea and the surrounding waters of Panthalassa streamed inland to replace it, carrying tremendous quantities of water vapor toward the coasts. Where those moisture-laden winds first encountered land, the atmosphere released its burden in powerful, seasonal downpours. Rivers swelled, floodplains expanded, and coastal environments experienced periods of abundant rainfall. These wet intervals did not last throughout the year. They belonged to a repeating seasonal pulse driven by the changing balance between land and sea, one that returned again and again across countless generations. When winter arrived, the pattern reversed. The immense continental interior lost its warmth far more rapidly than the surrounding ocean. Dense, cool, dry air settled across the land and spread outward toward the coastlines. Winds that had once carried moisture inland now flowed in the opposite direction. Regions that had received seasonal rains during summer entered prolonged dry periods as air streamed seaward from the heart of the continent. Farther inland, conditions changed very little between these opposing seasons because there was scarcely any moisture available to begin with. The central regions lay so distant from every coast that rain-bearing air masses exhausted most of their water long before reaching the interior. Atmospheric circulation, known as Hadley cells, which today help sustain tropical rainforests near the equator, interacted differently across the enormous supercontinent. Climate models indicate that these circulation patterns merged in ways that established a broad, arid belt across central Pangea, placing desert conditions where lush tropical forests might otherwise have flourished. The rocks preserve this remarkable climate with exceptional clarity. The towering sandstone cliffs that now define Zion National Park began as an immense field of wind, sculpted dunes during the Triassic period. Layer upon layer of drifting sand accumulated until deposits, thousands of feet thick, covered the landscape. Their sweeping internal structures reveal powerful, prevailing winds that repeatedly reshaped the desert. Some dunes exceeded those found in the modern Sahara, reflecting an environment molded by the persistent circulation of the megamonsoon. Additional evidence appears in extensive layers of salt and gypsum scattered through rocks formed during the Permian and Triassic periods. These minerals accumulated after shallow bodies of water repeatedly evaporated beneath intensely dry conditions, leaving dissolved materials behind as solid deposits. Their widespread distribution matches the pattern predicted by atmospheric models, providing another independent record of the climate that dominated central Pangea. As the supercontinent reached its greatest extent during the Triassic, the megamonsoon also reached its greatest strength. Simulations built from modern atmospheric physics indicate that seasonal temperature differences across the continental interior may have exceeded those experienced by any other extensive land surface in Earth's history, leaving their imprint across a landscape whose weather operated on a truly planetary scale. Traveling across Pangea from its dry continental center toward the eastern margin meant crossing into an entirely different world. Dust gave way to rivers. Broad plains opened into winding coastlines. Warm water stretched across the horizon, sheltered within the embrace of the supercontinent. Here, along the shores of the Tethys Sea, life flourished with a richness that stood in remarkable contrast to the arid landscapes farther inland. The Tethys remained consistently warm because surrounding land limited its exchange with the cooler waters of Panthalassa. In many regions, surface temperatures stayed above 86 degrees Fahrenheit throughout much of the year. Its shallow depths allowed sunlight to penetrate almost to the sea floor across enormous areas, providing ideal conditions for photosynthetic organisms that formed the foundation of thriving marine communities. Energy from the sun flowed efficiently through this ecosystem, supporting an abundance of life from the smallest drifting organisms to the largest predators of the sea. Reef systems spread across extensive stretches of the coastline. Unlike the coral reefs familiar today, many of these ancient structures were built by rugose corals and tabulate corals, groups that disappeared long ago. Brachiopods covered portions of the seafloor in extraordinary numbers, while crinoids anchored themselves like living gardens, filtering food from passing currents with delicate feathery arms. Ammonites drifted through the open water in beautifully coiled shells, representing one of the most successful groups of marine animals in Earth's history. Countless additional invertebrates occupied every available niche, creating ecosystems of remarkable complexity. The geography of the Tethys contributed greatly to this diversity. Tropical shallows, deeper offshore waters, temperate margins, and regions approaching cooler latitudes remained connected within one broad marine system. Organisms expanded, adapted, and dispersed through habitats that blended into one another across thousands of miles. Few oceans of comparable size have offered such a wide range of ecological settings linked within a single continuous environment. Life also prospered where rivers entered the sea. Water flowing from distant mountain belts carried sediments rich in dissolved minerals and organic material, spreading nutrients across coastal plains and shallow bays. Wetlands developed along river mouths, while forests covered nearby lowlands where rainfall remained dependable. Fish thrived in winding channels, amphibians occupied marshes, and terrestrial animals gathered where fresh water met the coast. These productive shorelines formed the biological heart of Pangea, supporting communities that differed greatly from those surviving deep within the continental interior. The influence of the Tethys extends far beyond its own age. Vast quantities of microscopic organisms, algae, and other marine life settled onto its seafloor after death, becoming buried beneath layer after layer of sediment. Over tens of millions of years, increasing pressure and heat transformed much of that organic material into petroleum. As Pangea gradually separated and the Tethys narrowed, these deposits remained trapped beneath younger rock formations. Many of the major oil fields of Saudi Arabia, Iraq, Kuwait, and Iran occupy regions that once lay beneath the waters of this vanished sea. The Tethys itself has nearly disappeared from the map. After Pangea broke apart, India began a long northward journey across the ocean before colliding with Asia, gradually closing the remaining eastern passage. One familiar body of water preserves a distant fragment of that older world. The Mediterranean Sea, enclosed by land on three sides, represents the last surviving remnant of a marine realm that once nourished one of the richest ecosystems Earth has ever known. Across the connected lands of Pangea, life reached a remarkable moment of balance around 270 million years ago. Forests covered favorable regions, rivers crossed broad plains, and animals occupied nearly every environment the supercontinent could provide. Although later ages would become famous for giant dinosaurs, they had not yet appeared. The dominant creatures of this world belonged to a different branch of the family tree, one that would eventually give rise to mammals, including ourselves. These animals were known as synapsids. At first glance, many resembled reptiles, with sprawling bodies, long tails, and scales covering much of their skin. Their deeper anatomy, however, placed them on a separate evolutionary path. Features of the skull, jaw, and teeth reveal that they shared a closer relationship with mammals than with living reptiles. During the Permian period, synapsids occupied an astonishing variety of ecological roles, from swift hunters to massive plant eaters, forming the foundation of nearly every land ecosystem across Pangea. Among the most recognizable was Dimetrodon, an animal that has often been placed beside dinosaurs in books, museums, and popular illustrations. That familiar pairing disguises a very different history. Dimetrodon disappeared roughly 40 million years before the earliest dinosaurs evolved. Reaching lengths of about 15 feet, it hunted other animals with powerful jaws lined by sharp teeth. Rising above its back stood a tall sail, supported by greatly elongated neural spines extending from the backbone. Most researchers conclude that this remarkable structure helped regulate body temperature, absorbing warmth during cool periods and releasing excess heat when conditions became much warmer across the strongly seasonal landscapes of Pangea. Other predators carried an appearance that seems surprisingly familiar today. Gorgonopsids possessed forward-facing eyes that improved depth perception, sturdy limbs that produced a gait resembling that of large mammals, and long saber-shaped canine teeth designed for seizing prey. Some individuals approached 10 feet in length, making them the dominant terrestrial hunters during the closing chapters of the Permian. Wherever large herbivores gathered, these predators followed, shaping animal populations through constant pursuit across the connected continent. The most widespread plant eaters belong to another successful lineage known as Dicynodonts. Their diversity was extraordinary. Some species remained scarcely larger than modern rats, while others rivaled the size of living rhinoceroses. Most possessed strong beak-shaped mouths, adapted for cropping vegetation, accompanied by a pair of tusks projecting from the upper jaw. Fossils of Dicynodonts have been recovered from every continent that once formed part of Pangea, demonstrating how thoroughly they occupied the available landscapes. They filled the ecological role later taken by many grazing and browsing mammals, converting abundant plant life into the energy that sustained entire food webs. One geographical reality shaped every struggle for survival during this age. Because Earth's major landmasses had merged into one continuous continent, populations remained connected across enormous distances. There were few barriers capable of isolating species for long periods. Successful adaptations spread widely, while competition extended across an immense, shared landscape instead of remaining confined to separate continents. Predators, herbivores, and scavengers participated in the first truly global terrestrial ecosystem that Earth had ever assembled, a living network stretching from one end of Pangea to the other, where every evolutionary advantage echoed across an entire world. Success can carry its own hidden cost. By the late Permian period, Pangea supported an extraordinary variety of environments and living communities spread across one immense connected landscape. Rivers linked distant regions, coastlines nourished thriving ecosystems, and animals moved across territory unmatched in Earth's earlier history. The same continuity that encouraged such biological richness also removed many of the natural barriers that normally protect life when conditions begin to change. On a world divided into separate continents, disasters often remain partly confined by geography. Oceans interrupt the spread of changing climates, diseases, invasive species, and environmental upheaval. Populations isolated from one another may survive even if neighboring regions suffer devastating losses. Separate landmasses provide refuges where evolution can continue, preserving lineages that later expand once favorable conditions return. Pangea offered far fewer opportunities for such separation. Every major terrestrial ecosystem belonged to one connected continent. The surrounding waters formed one global ocean. Winds circulated through a unified atmosphere, while climatic shifts spread across immense distances without encountering the interruptions created by multiple ocean basins and isolated continents. Ecological change in one region could ripple outward through connected habitats until its influence reached nearly every corner of the planet. The geography of the coast had also changed profoundly during the formation of the supercontinent. As continents merged, countless smaller shorelines disappeared. Inland seas that had once occupied spaces between drifting landmasses gradually vanished as collisions welded continents together. Each disappearing coastline represented the loss of shallow marine habitat, environments where sunlight reached the seafloor and abundant oxygen supported exceptionally productive communities. These coastal waters had sustained repeated waves of marine diversification throughout much of the Paleozoic era. Their reduction carried lasting ecological consequences. Reef systems became concentrated into fewer suitable locations, while species adapted to stable, well oxygenated shallow seas occupied increasingly limited ranges. Many organisms depended upon conditions found only along continental shelves, where nutrients, sunlight, and circulating water combined to create productive ecosystems. As those habitats contracted, opportunities for relocation diminished. Entire communities became tied to relatively small portions of the global coastline. The immense waters of Panthalassa offered little compensation for those losses. Its great size limited vigorous circulation across broad regions, reducing the continual mixing that characterizes the oceans of today. Water exchange occurred, yet much of the basin remained comparatively sluggish over long periods. Marine ecosystems adapted to stable conditions developed within a world already possessing fewer environmental alternatives than earlier geological ages had provided. Life on land faced a comparable circumstance. Connected habitats encouraged widespread distributions, allowing successful species to occupy enormous territories. That same success reduced isolation. Distinct populations mixed more readily, and ecological networks extended across the breadth of the supercontinent. When environments shifted, there were fewer distant landscapes beyond the reach of those changes. The planet had become biologically interconnected on a scale unmatched before or afterward. By the close of the Permian period, Earth's living systems remained abundant, yet the structure supporting them had grown increasingly delicate. Coastlines had contracted, shallow marine habitats had declined, ecological connections stretched across a single continent, and one atmosphere linked every landscape beneath the same sky. The world possessed remarkable unity, though that unity carried an unexpected weakness. When profound disruption finally arrived around 252 million years ago near Pangea's northern reaches, the pathways that had once connected life also carried catastrophe across an entire planet with extraordinary efficiency. At the northern edge of Pangea, the ground began to open in a way unlike the eruption of any familiar mountain. There was no single towering cone dominating the horizon, no isolated summit releasing a brief outburst before returning to stillness. Around 252 million years ago, an immense region of what is now Siberia fractured across hundreds of miles. Molten rock rose through countless openings, beginning a volcanic episode that endured for nearly 1 million years. Geologists know this region as the Siberian Traps. The name comes from the Swedish word meaning stairs, chosen to describe the broad steppe landscape left behind as one lava flow spread across another. Layer accumulated upon layer until the volcanic province covered roughly 770,000 square miles, an expanse comparable to much of Western Europe. In some places, the hardened lava reached nearly 1 2/10 miles in thickness. This was not a single eruption preserved in stone. It was the gradual transformation of an entire region through repeated pulses of volcanic activity. Those pulses reshaped far more than the landscape surrounding the vents. Each phase released immense quantities of carbon dioxide and sulfur dioxide into the atmosphere, together estimated between 14 trillion and 48 trillion tons over hundreds of thousands of years. Activity did not proceed without interruption. Periods of relative calm separated renewed surges, allowing one environmental disturbance to settle before another arrived. The planet entered a prolonged sequence of changes instead of experiencing one brief catastrophe. The earliest global response came through the atmosphere itself. Carbon dioxide trapped increasing amounts of heat, raising temperatures across land and sea. As the oceans warmed, they became less capable of holding dissolved oxygen. Marine animals that had evolved within cooler, oxygen-rich water encountered conditions that steadily reduced the supply of one resource every complex organism requires. Habitats that had remained stable across immense spans of time gradually became harder to survive. Another transformation unfolded within the seawater. Carbon dioxide dissolved into the oceans and formed carbonic acid, altering the chemistry upon which many marine organisms depended. Creatures that built shells or supporting skeletons from calcium carbonate faced increasing difficulty maintaining those structures. Reef communities, already reduced during the formation of the supercontinent, found themselves under growing chemical stress as the foundations supporting countless marine food webs weakened. Volcanic gases carried additional consequences into the upper atmosphere. Among them were compounds containing chlorine and bromine, elements that modern atmospheric modeling identifies as capable of damaging the ozone layer. As that protective shield diminished, greater amounts of ultraviolet radiation reached Earth's surface. Organisms adapted to previous conditions, encountered levels of exposure that exceeded what many species could tolerate over extended periods. The evidence that these events spread across the entire planet remains preserved within rocks formed at the extinction boundary. Mercury, an element commonly associated with major volcanic activity, appears in geological formations on every continent that once belonged to Pangea. Identical chemical signatures have been discovered thousands of miles from Siberia, including southern regions separated from the eruption site by nearly 8,000 miles. The volcanic signal traveled through one connected atmosphere shared by every landscape and every ocean. Distance offered no lasting refuge because the world itself had become a single interconnected system through which every pulse eventually reached all life. The transformation unfolded without a single defining moment that separated one world from the next. Generation after generation, familiar species disappeared until the living fabric of Pangea no longer resembled the one that had flourished before. What paleontologists now call the Great Dying remains the most severe biological crisis ever recorded in Earth's history. Approximately 96% of marine species vanished. Around 70% of terrestrial vertebrate species disappeared. Some scientific estimates place the total loss above 90% of all species then living on the planet. Measured beside later extinctions, the scale becomes even clearer. The asteroid impact that ended the reign of the non-avian dinosaurs about 66 million years ago eliminated roughly three-quarters of Earth's species. That catastrophe permanently reshaped life, yet it did not approach the magnitude of the Permian extinction. During the Great Dying, there was no impact from space. The collapse emerged from processes unfolding within Earth itself, spreading across a world whose environments had become deeply interconnected. The oceans suffered first and most intensely. Geological evidence indicates that the principal phase of marine extinction may have unfolded in less than 60,000 years, scarcely an instant on the timescale of Earth's history. Entire reef communities disappeared, followed by countless shell-bearing animals, predators, scavengers, and microscopic organisms that formed the foundation of marine food webs. The losses moved through every level of the ecosystem until the structures supporting complex ocean life gave way. Conditions on land changed across a longer interval. Instead of one abrupt collapse, ecosystems experienced repeated waves of decline extending through hundreds of thousands of years. Plant communities contracted, animal populations dwindled, and ecological relationships that had endured for millions of years gradually unraveled. Recovery in one region could be interrupted by another environmental disturbance before stability had returned, leaving surviving organisms to endure a prolonged period of uncertainty. Among the most remarkable records of this transition lies hidden within layers of ancient sediment. Fossil pollen from established forest trees dominates one layer, then almost disappears in the next. Replacing it is an extraordinary abundance of fungal spores. Geologists refer to this unmistakable signal as the fungal spike. It marks a time when decomposers spread through forests filled with fallen trunks and decaying vegetation faster than new woodland could become established. The rocks preserve this shift with striking clarity, capturing the moment when decomposition briefly overwhelmed renewal across immense landscapes. The oceans entered an equally unusual state after the principal extinction pulse had passed. Fossil-bearing rocks reveal an extended interval, sometimes described as a biological dead zone, lasting perhaps hundreds of thousands of years. New species appeared only rarely. Empty ecological roles remained vacant long after earlier inhabitants had vanished, the sea had not merely lost its diversity. Many of the interactions that sustained complex marine ecosystems had broken down, requiring millions of years before evolutionary processes rebuilt them. Across Pangea, the consequences reached every major group of organisms. Forests diminished, many plants disappeared, insects declined, amphibians suffered enormous losses, and the powerful synapsid dynasties that had dominated the Permian entered irreversible decline. Gorgonopsids vanished entirely. Most dicynodont lineages disappeared. Predator and prey communities that had stretched across the supercontinent dissolved into scattered remnants. The first truly global terrestrial ecosystem in Earth's history survived only as isolated fragments, leaving a planet whose living richness had been reduced to a faint echo of its former abundance. When the Great Collapse had finally spent its force, the landscapes of Pangea no longer belonged to the rich communities that had once filled them. Forests were diminished, food webs had unraveled, and many familiar animals had vanished forever. Across this altered continent, one unassuming creature appeared with remarkable consistency. It possessed neither imposing size nor formidable weapons. By appearance alone, few would have predicted that it would become the defining land animal of the early Triassic period. Its name was Lystrosaurus, derived from Greek words meaning shovel reptile, a reference to the broad shape of its snout. Despite that traditional name, it belonged to the dicynodont branch of synapsids, the same broader lineage that stood closer to mammals than to modern reptiles. Standing only about 3 feet long and weighing roughly as much as a large dog, it carried a sturdy body supported by strong limbs, a beak suited for cropping vegetation, and a pair of modest tusks projecting from the upper jaw. Before the extinction, it had been only one member among many herbivores scattered across Pangea. Afterward, it became almost everything. Fossil discoveries reveal the astonishing scale of that success. Remains of Lystrosaurus have been uncovered in what are now South Africa, Antarctica, India, Russia, and China, along with additional regions once joined within the supercontinent. Today, these discoveries lie on widely separated continents, yet during the early Triassic they formed one continuous landmass. Lystrosaurus did not cross oceans or island chains. It walked across connected terrain, expanding into habitats left vacant by the disappearance of countless competitors. Its survival continues to inspire scientific debate because no single explanation fully accounts for its extraordinary persistence. One possibility centers on its burrowing behavior. Underground shelters may have protected individuals from severe environmental fluctuations that swept across the surface during the worst phases of the extinction. Fossils recovered from Antarctica provide another intriguing clue. Growth patterns preserved within tusks suggest intervals when normal development slowed dramatically, a feature consistent with a hibernation-like state of torpor that could have conserved energy during prolonged periods of cold or limited food availability. Diet may also have played an essential role. The powerful beak of Lystrosaurus could process coarse vegetation that many other herbivores found difficult to consume. In ecosystems where nutritious plants had become scarce, the ability to survive on tougher, lower quality food may have offered a decisive advantage. Survival depended less upon speed or strength than upon enduring conditions that defeated more specialized animals. Once the extinction had removed roughly 70% of terrestrial vertebrate species, the ecological landscape changed beyond recognition. Predators became uncommon across broad regions, while empty habitats stretched across the connected continent. Lystrosaurus expanded into those vacant environments with remarkable success. It did not require dramatic anatomical innovation or the emergence of an entirely new form. The opportunities already existed, with competition greatly reduced and barriers between regions almost non existent. Populations spread across Pangea until this modest herbivore came to represent an estimated 95% of all land vertebrates known from parts of the early Triassic fossil record. Its story illustrates that survival and dominance are not always achieved by the largest or most formidable creatures. Sometimes they belong to the species capable of enduring when nearly everything else has disappeared, carrying life forward across a transformed world until diversity slowly begins to return. For millions of years after the extinction reached its greatest intensity, the land did not spring back to life. Recovery moved at a pace almost impossible to appreciate within a human lifetime. The early Triassic period, spanning roughly 5 million years after the Great Dying, remains one of the least understood chapters in Earth's history because so little survived to leave a record behind. Rocks from this interval preserve scattered glimpses instead of thriving ecosystems, revealing a continent where biological complexity had been stripped to its bare framework. The fossil evidence reflects that emptiness with striking consistency. Lystrosaurus appears again and again across deposits formed on different parts of Pangea, accompanied by only a modest collection of other survivors. Instead of diverse communities containing many specialized animals, paleontologists find simplified ecosystems dominated by hardy generalists capable of enduring harsh conditions. Entire branches of the evolutionary tree that had flourished during the Permian were absent, leaving ecological roles either vacant or occupied by a handful of adaptable species. Large terrestrial predators had almost disappeared. The gorgonopsids that once ruled food chains were gone forever. Most of the great dicynodont herbivores had vanished alongside them, taking with them the intricate relationships that had linked hunters, grazers, scavengers, and decomposers into balanced communities. A Lystrosaurus wandering across broad stretches of the early Triassic landscape may have encountered remarkably few threats capable of bringing its life to an end. Paleontologists do not describe this interval as one of extraordinary abundance. They describe it as a world reduced to unusual ecological simplicity, where diversity had not yet found a path back. Environmental conditions offered little encouragement for rapid recovery. The megamonsoon continued shaping seasonal extremes across the supercontinent, while the warming initiated by the Siberian Traps persisted long after the greatest eruptions had subsided. Scientific estimates indicate that average global temperatures during portions of the early Triassic stood roughly 14 to 18 degrees Fahrenheit, higher than those of the modern world. Near the equator, portions of the ocean may have reached temperatures approaching 104 degrees Fahrenheit, nearing the upper thermal limits tolerated by many forms of complex marine life. Vegetation struggled to regain its former extent. The forests that had once occupied favorable regions along Pangea's coastal margins did not immediately return after the extinction. Instead, many landscapes appear to have been covered by opportunistic plants that could establish themselves rapidly on disturbed ground. Ferns and horsetails spread across broad areas, while longer-lived forest communities remained scarce. Soil formation, nutrient cycling, and the intricate relationships between plants and animals all required time to rebuild after such profound disruption. These simplified environments endured across thousands of generations. Evolution continued, though it advanced through ecosystems far less crowded than those that had existed before the extinction. Empty habitats remained available, competition was reduced, and ecological opportunities persisted across a connected continent still recovering from its greatest biological crisis. Within this altered world, new evolutionary experiments gradually appeared among the surviving reptiles. They emerged upon landscapes that had lost much of their previous complexity, where vacant ecological roles extended across immense distances. The first dinosaurs entered a planet that offered neither the flourishing richness of the Permian nor the abundance familiar from later ages. They inherited a world still recovering, where the long process of rebuilding Earth's living tapestry had only just begun. New branches of life rarely announce themselves with grandeur. They often begin as modest experiments, occupying overlooked corners of ecosystems, while larger, more established creatures command attention. During the Middle Triassic period, about 243 million years ago, such an experiment appeared on the connected lands of Pangea. Fossils discovered in what are now Argentina and Tanzania preserve some of the earliest confirmed dinosaurs, though at that time those distant regions formed parts of one uninterrupted continent joined by thousands of miles of dry land. These pioneering dinosaurs bore little resemblance to the colossal animals that would later become symbols of the Mesozoic era. Among the earliest known was Eoraptor, a lightly built animal measuring about 3 feet in length and weighing less than 20 pounds. It balanced on two slender legs, carried grasping hands, and possessed a body designed for agility. Its teeth suggest a flexible diet, allowing it to feed upon whatever resources were available. Nothing in its appearance hinted that descendants of creatures like this would one day dominate terrestrial ecosystems for roughly 165 million years. The world they entered remained far from stable. Ecological communities were still rebuilding after the devastation that had reshaped life across Pangea. Numerous evolutionary lineages competed to occupy the empty habitats left behind by vanished species. Dinosaurs represented only one among several groups, exploring those opportunities, sharing the landscape with a remarkable variety of archosaurs whose own histories seemed equally promising. Among these rivals were armored atosaurs that browsed across the land, crocodile-shaped phytosaurs that hunted in rivers and lakes, and towering Rawasuchians that became formidable terrestrial predators. Each group displayed distinctive adaptations suited to the recovering world. For much of the Triassic, there was little indication that dinosaurs possessed any overwhelming advantage. Their populations remained comparatively modest, and they occupied only a fraction of the ecological roles available across the supercontinent. Connection, however, continued to shape evolution in subtle ways. Because Pangea still formed one continuous landmass, successful species could expand across immense distances without encountering oceans that divided populations. Fossils of later Triassic dinosaurs appear across regions that would eventually become separate continents, revealing that these adaptable animals gradually dispersed through much of the connected world. Their spread reflected geography as much as biology. A favorable adaptation arising in one part of Pangea could move steadily across neighboring environments through countless generations. This broad distribution also encouraged genetic exchange between populations over ranges impossible on a fragmented planet. Evolutionary innovations did not remain confined within isolated continents for millions of years. They traveled with migrating animals, allowing successful body plans to establish themselves across varied climates and landscapes. Small differences accumulated from place to place, yet the connected continent provided pathways through which expanding lineages could continue exploring newly available habitats. For millions of years, the contest remained unresolved. Dinosaurs persisted, diversified gradually, and shared their world with competitors that often appeared equally successful. They were participants in an evolutionary experiment rather than its unquestioned winners. Their future dominance depended upon circumstances that had not yet unfolded, while Pangea itself remained largely intact beneath their wandering feet. Across that immense connected landscape, both the continent and its rising inhabitants approached another turning point that would transform their histories together. Every supercontinent carries within it the forces that will eventually divide it again. For tens of millions of years, Pangea had remained joined across a single, immense landmass, yet deep beneath its surface, slow movements within Earth's mantle continued reshaping the planet. Around 201 million years ago, those hidden forces reached a new stage. Long fractures opened through the crust where a future ocean would one day exist, and volcanic activity spread along a growing rift that marked the beginning of Pangea's separation. Geologists call this immense volcanic system the Central Atlantic Magmatic Province. Although smaller than the Siberian Traps, its position gave it extraordinary importance. Instead of erupting within the interior of an already assembled continent, it developed along the line where the crust itself was being stretched apart. Molten rock rose through countless fissures, producing extensive flood basalts, while the land slowly yielded to forces acting far below. The eruptions accompanied the birth of an entirely new ocean basin. The evidence remains preserved across continents, now separated by thousands of miles of water. Matching volcanic rocks appear in present-day Morocco, the Iberian Peninsula, eastern North America, and the Amazon basin of South America. Their chemical composition closely matches, and radiometric dating places them within the same interval around 201 million years ago. These scattered formations were once parts of one continuous volcanic province before continental drift gradually carried them apart. The Atlantic Ocean now occupies the space where those connected lava fields once stretched without interruption. Environmental consequences soon spread beyond the rift itself. Repeated eruptions released large quantities of volcanic gases into the atmosphere, disrupting climate and ocean chemistry during a period already marked by ecological instability. This volcanic episode coincided with the end Triassic extinction, an event that eliminated roughly 76% of all species. Once again, Earth's living systems experienced widespread losses, though the destruction remained less severe than the great dying that had reshaped the preceding era. Several dominant groups that had flourished throughout the Triassic disappeared during this extinction. Dinosaurs vanished from the fossil record. Phytosaurs, whose crocodile-like bodies had occupied rivers and wetlands, also disappeared. Rauisuchians, formidable predators that had rivaled the largest land animals of their time, met the same fate. These lineages had shared recovering ecosystems with early dinosaurs for millions of years, competing for food, territory, and opportunity across the connected supercontinent. Dinosaurs survived while many of their principal competitors did not. Paleontologists continue debating the reasons behind that survival, exploring differences in physiology, growth, reproduction, and ecological flexibility. Whatever combination of traits proved decisive, the outcome transformed terrestrial life. As the Jurassic period began, dinosaurs expanded into ecological roles left vacant by extinction, becoming the dominant land vertebrates across much of the planet. The volcanic province also accomplished something beyond biological change. Stretching crust eventually thinned enough for seawater to enter the widening depression between separating continental blocks. At first, this new body of water formed only a narrow rift sea, resembling the modern Red Sea far more than today's Atlantic Ocean. Gradually, the opening lengthened and broadened as tectonic motion continued pulling the continents apart. The continent that had allowed animals to roam from one end of the world to the other had begun to separate along its center. The same geological forces that reshaped life after the end, Triassic extinction, also initiated the long process through which Pangea dissolved, replacing one connected world with oceans that would once again divide Earth's continents. Continents rarely part with sudden motion. Their separation unfolds so gradually that no living creature could witness the entire process. Yet the rocks preserve each stage with remarkable precision. Beneath every modern ocean lies a chronological archive written into cooling volcanic crust. As new seafloor formed, minerals aligned themselves with Earth's magnetic field, creating a sequence of alternating patterns that now allows geologists to reconstruct the slow dissolution of Pangea across roughly 100 million years. The earliest chapter began about 200 million years ago. A widening rift gradually divided the supercontinent into two immense landmasses. To the north lay Laurasia, containing the foundations of what would later become North America, Europe, and much of Asia. Farther south stretched Gondwana, carrying the future continents of South America, Africa, Antarctica, Australia, and India. Between these expanding halves, the first waters of the central Atlantic entered a narrow opening that would continue widening through countless generations. Division did not end there. Gondwana itself remained united only for a time before fresh fractures developed within its interior. Africa and South America stayed connected until about 130 million years ago, when the South Atlantic began opening. Geological evidence indicates that this separation started near the southern end of the continents before extending steadily northward. Year after year, the widening measured only inches, a pace imperceptible within a human lifetime, yet sufficient to produce an ocean across millions of years. Coastlines that once formed neighboring shores slowly drifted beyond one another's horizon. India followed an especially remarkable path. After separating from Antarctica, it embarked upon a long northward journey across the waters that had once occupied the Tethys Sea. Covering nearly 3,000 miles over roughly 60 million years, the Indian continental plate traveled unusually rapidly for a tectonic block. During its fastest interval, it advanced at close to 6 inches each year, carrying entire landscapes toward an eventual meeting with Asia that would reshape another chapter of Earth's geological history. Far to the south, Antarctica and Australia remained connected much longer than many of the other continental fragments. Their partnership endured until about 45 million years ago, when the final separation created new marine passages surrounding Antarctica. The opening of these southern waterways allowed ocean currents to circulate freely around the continent, isolating it from warmer waters arriving from lower latitudes. This reorganization altered global climate patterns, encouraging the long development of the immense Antarctic ice sheets that would later influence sea levels and atmospheric circulation across the planet. Each stage of continental separation left an enduring mark upon Earth's geography. The Atlantic Ocean records the earliest division between Laurasia and Gondwana. The Indian Ocean reflects India's departure from the southern supercontinent. The Southern Ocean preserves the final isolation of Antarctica. Every expanding basin traces the route of an ancient fracture that once cut through continuous land. Modern maps therefore carry an older story beneath their familiar outlines. Continents that appear permanently separated today still preserve matching mountain belts, rock formations, and fossil distributions inherited from their shared past. The oceans between them are not empty spaces created without history. They are enduring records of Pangea's gradual transformation, where the memory of one connected world remains written across the surface of the sea. Isolation can reshape life as profoundly as extinction. Once a continent drifts beyond the reach of its neighbors, evolution begins following pathways that no longer need to match the rest of the planet. Around 45 million years ago, Australia completed its separation from Antarctica. From that point onward, the surrounding seas became barriers that few land animals could cross. An entire biological community continued its history in remarkable independence, preserving lineages that would fade almost everywhere else. Among the most distinctive inhabitants were the marsupials. These mammals give birth while their young remain at a very early stage of development, with growth continuing inside an external pouch. Their ancestors had once occupied broad portions of the ancient southern continents, descendants of populations that ultimately traced their history back to Pangea. During the following millions of years, placental mammals expanded across Africa, Europe, Asia, North America, and South America, diversifying into an extraordinary variety of forms. Australia, however, remained separated from those expanding lineages by open ocean. That prolonged isolation altered the balance of evolution. Across much of the world, placental mammals became the dominant land mammals, occupying an enormous range of ecological roles. Australia followed a different course. Marsupials diversified into forms that fulfilled many of the same functions performed elsewhere by unrelated placental species. Similar ecological challenges repeatedly encouraged similar body plans, even though the animals belonged to entirely different branches of the mammalian family tree. Kangaroos developed powerful hind limbs suited for traveling efficiently across open country, becoming the principal grazing mammals over large regions. Wombats evolved sturdy bodies and impressive digging abilities, creating extensive burrow systems beneath the soil. The Tasmanian devil became an important scavenger and predator, consuming carrion as well as smaller prey. The thylacine, often called the Tasmanian tiger because of the stripes across its back, occupied the role of an apex predator before its extinction during the 20th century. None of these animals descended from wolves, deer, rodents, or other familiar placental mammals. Their similarities arose through convergent evolution as different evolutionary lineages arrived at comparable solutions to comparable ecological demands. Australia also preserved an even older mammalian heritage. The monotremes, represented today by the platypus and echidnas, remain the only living mammals that lay eggs. Their ancestors separated from other mammalian lineages long before marsupials and placental mammals diverged from one another. Elsewhere, these early branches disappeared through changing environments and competition. Australia's isolation provided conditions in which they continued surviving while retaining reproductive characteristics inherited from some of the earliest mammals. The continent, therefore, became more than a place distinguished by unusual wildlife. It preserved evolutionary histories that had largely vanished elsewhere, allowing scientists to compare living representatives of ancient lineages with mammals that followed very different paths on other continents. Every surviving marsupial and monotreme contributes another chapter to that long record of separation. The roots of this extraordinary diversity reach back to the gradual fragmentation of Pangea. When Australia drifted away from Antarctica, it carried with it a distinctive collection of animals whose descendants continued evolving in relative isolation for tens of millions of years. Modern coastlines, oceans, and ecosystems still reflect that ancient separation, demonstrating that the movement of continents can influence the direction of evolution long after the rocks themselves have fallen still. A rearrangement of continents becomes, with enough time, a rearrangement of air, water, and seasons. As Pangea dissolved, Earth inherited more than new coastlines. The planet acquired an entirely different climate system, one built from expanding oceans, changing currents, and shifting pathways for heat. The transformation unfolded gradually, yet its influence continues shaping weather, ecosystems, and temperatures across the globe today. While the supercontinent remained intact, one immense ocean dominated the planet. Its circulation was comparatively simple, with fewer barriers to redirect moving water. Broad regions far from the coast experienced prolonged dryness, while seasonal rains concentrated elsewhere beneath the influence of the great continental monsoon. As new ocean basins widened between separating landmasses, those patterns steadily lost their former structure. Water gained additional routes through which it could exchange heat, nutrients, and dissolved gases across the planet. One of the most significant changes occurred after Antarctica became completely isolated from neighboring continents. Australia drifted away first, followed later by the final separation between Antarctica and South America. When these continental connections disappeared, an uninterrupted marine passage encircled Antarctica for the first time. Through this opening developed the Antarctic Circumpolar Current, an immense river of seawater flowing continuously around the southern continent. Unlike most ocean currents, it encountered no continental barrier capable of stopping its journey. That uninterrupted circulation profoundly altered the movement of heat. Warmer waters from lower latitudes could no longer reach Antarctica with the same efficiency. As the southern continent became increasingly isolated from external warmth, temperatures declined across its interior. Geological evidence shows that Antarctica had once supported forests, with fossil wood, leaves, and pollen revealing landscapes occupied by temperate trees. Around 34 million years ago, expanding ice sheets began covering the continent, marking the beginning of the frozen environment that now defines Earth's southern pole. Elsewhere, the growing Atlantic Ocean, the Indian Ocean, and the Southern Ocean established increasingly intricate patterns of circulation. Water masses with different temperatures and salinity interacted across expanding basins, creating a far more dynamic planetary system than had existed during the age of Panthalassa. One important component became thermohaline circulation, a worldwide network driven by differences in water density. Warm, salty water travels across the surface before cooling and sinking in colder regions, while deeper currents eventually return toward lower latitudes. This continuous exchange redistributes heat across vast distances and helps stabilize Earth's long-term climate. Continental fragmentation also reshaped marine habitats. A single supercontinent possesses relatively little coastline compared with many separate continents. As Pangea divided, the combined length of continental margins increased dramatically. Extensive shallow seas developed along these new shores, creating favorable environments for coral reefs, shellfish, fishes, and countless other marine organisms. These coastal ecosystems supported increasingly complex food webs and provided opportunities for diversification across many branches of ocean life. The flourishing marine communities that characterize much of the Cenozoic era, therefore, owe part of their success to geological change that began long before humans existed. Every expanding shoreline, every newly formed current, and every polar ice sheet traces its origin to continents drifting apart across deep time. Earth's modern climate did not emerge by chance. It developed through the gradual reorganization of oceans and land, preserving within today's winds and waters the enduring legacy of Pangea's slow dissolution. A coastline is more than the meeting place of land and sea. For animals unable to cross open water, it marks the edge of an evolutionary world. As the fragments of Pangea drifted farther apart, each widening ocean became a barrier that redirected the history of life. Populations once linked by continuous landscapes grew isolated from one another, accumulating differences across millions of years until entirely distinct faunas emerged on separate continents. South America provides one of the clearest examples of this long separation. For much of the Cenozoic era, it remained isolated from North America by the Central American Seaway. During that extended interval, mammals evolved along paths unlike those followed elsewhere. Ground sloths reached enormous sizes, with some growing as large as modern elephants. Glyptodonts developed heavy, armored shells, transforming into creatures that resembled living fortresses and reached the size of small automobiles. Litopterns acquired slender limbs and graceful proportions, remarkably similar to horses, although their ancestry lay within a completely different branch of mammals. Toxodonts possessed robust bodies that invited comparison with rhinoceroses, despite sharing no recent relationship with them. Similar forms emerged because comparable environments encouraged comparable adaptations, even when evolutionary origins remained separate. This distinctive community persisted for roughly 60 million years. When tectonic activity eventually raised the Isthmus of Panama about 3 million years ago, the barrier between North and South America disappeared. Animals that had evolved independently for immense spans of time encountered one another across connected landscapes. Species from both continents expanded into unfamiliar territory, initiating what paleontologists call the Great American Biotic Interchange. The consequences unfolded unevenly. Several groups from North America established successful populations across the southern continent, while comparatively fewer South American mammals expanded permanently into the north. Many characteristic southern lineages declined during the following interval, influenced by increasing competition, changing environments, and later human arrival. Although extinction resulted from multiple interacting causes, the renewed continental connection fundamentally altered ecological relationships that had remained separate for tens of millions of years. Far across the Indian Ocean, Madagascar tells another story shaped by prolonged isolation. Having separated from Africa about 90 million years ago, the island developed biological communities unlike those found anywhere else. Lemurs diversified into numerous forms, occupying forests, dry woodlands, and rocky landscapes, becoming the island's dominant primates. Tenrecs evolved into an astonishing variety of shapes, despite descending from a relatively small ancestral population. The fossa emerged as Madagascar's largest native predator, filling ecological roles occupied elsewhere by very different carnivorous mammals. Each lineage reflects an evolutionary history conducted apart from neighboring continents. These examples illustrate a pattern repeated throughout Earth's geological past. Separation encourages diversification by allowing populations to adapt independently to local conditions. When those isolated worlds reconnect after immense intervals, the encounter often produces sweeping ecological change. Species that evolved under different competitive pressures suddenly share the same habitats, and established balances may shift with surprising speed. The Great American Biotic Interchange offers scientists an especially detailed opportunity to examine this process because it occurred comparatively recently and left an abundant fossil record. Yet the principle extends far beyond the Americas. Throughout the long aftermath of Pangea's fragmentation, every new ocean redirected the course of evolution, while each renewed connection reshaped living communities once again. The geography of the modern world continues carrying the biological consequences of continents that first drifted apart across deep time. Among the countless branches of life's history, one slender thread extends without interruption across an immense span of time. It passes through changing continents, shifting climates, volcanic upheavals, and repeated extinctions, never beginning again, never starting over. Every complex land animal living today belongs to that continuous inheritance. However different their forms may appear, each traces its ancestry to survivors that endured the Great Dying while Pangea still united the world's land. The lineage leading to mammals reaches even farther into the past. Mammals belong to the synapsids, an ancient branch of vertebrates whose early members appeared long before the first dinosaurs. Familiar creatures such as Dimetrodon and the Dicynodonts formed part of this extended family, representing evolutionary experiments that flourished across Permian landscapes. Around 270 million years ago, synapsids already occupied environments spread across Pangea, adapting to forests, floodplains, and dry interior regions, while the supercontinent remained whole. The earliest true mammals emerged much later during the late Triassic. They were modest animals, often no larger than modern shrews, feeding upon insects beneath vegetation and fallen branches. Their lives unfolded alongside reptiles that dominated the visible landscape, leaving mammals to occupy ecological opportunities requiring small size, rapid movement, and activity during darker hours. Although they attracted little attention compared with the giant reptiles surrounding them, these unobtrusive creatures carried anatomical innovations that would eventually shape an extraordinary future. As Pangea gradually fragmented, those early mammalian populations traveled with the separating continents. Geography began guiding evolution in different directions. Across northern landmasses, one collection of lineages eventually produced the placental mammals. Southern continents preserved populations that developed into marsupials, while Australia's prolonged isolation safeguarded the monotremes, descendants of an even older mammalian branch. Each continental fragment became a separate setting in which inherited characteristics mixed with new environmental pressures, producing the remarkable diversity recognized today. For more than 100 million years, mammals remained secondary participants within ecosystems dominated by dinosaurs. Their persistence during that immense interval reflects endurance rather than abundance. Then, about 66 million years ago, an asteroid struck near the present-day Yucatan Peninsula, initiating the Cretaceous Paleogene extinction. The disappearance of the non-avian dinosaurs transformed ecological communities across the globe. Habitats that had long been occupied by giant reptiles became available to surviving mammals, opening opportunities that had scarcely existed before. Evolution responded with extraordinary speed on geological timescales. Within roughly 10 million years, mammalian descendants diversified into forms adapted for oceans, forests, grasslands, and the open sky. Some became whales, navigating coastal waters and the deep sea. Others evolved into bats, capable of sustained flight. Additional branches produced horses, elephants, primates, and countless other lineages, occupying nearly every terrestrial environment. The evolutionary potential carried by those small Triassic mammals finally expanded across a world no longer ruled by dinosaurs. One branch of the primates eventually arose in Africa, itself a fragment of Gondwana that had once formed part of Pangea. From that continent emerged the lineage leading to human beings, linked through uninterrupted ancestry to synapsids that crossed Permian landscapes hundreds of millions of years earlier. The path remained continuous through catastrophe, continental separation, and biological transformation. Every person alive today carries that same unbroken connection, extending from the shores of an ancient supercontinent to the present Earth that grew from its gradual dissolution. Knowledge of Pangea has grown through generations of fieldwork, laboratory analysis, and discoveries scattered across every continent. Even so, some chapters remain unfinished. Fossils preserve only fragments of vanished ecosystems, rocks record events unevenly, and many geological processes erase parts of their own history. The result is a picture of remarkable clarity in many places, accompanied by areas where evidence remains incomplete or points toward more than one interpretation. Those uncertainties continue guiding research instead of diminishing it. One enduring discussion concerns the climate deep within Pangea. Many studies support the megamonsoon hypothesis, in which the enormous supercontinent generated seasonal shifts of exceptional intensity. Geological indicators, including ancient soils and sedimentary layers, agree with this interpretation across extensive regions. At the same time, evidence collected from Triassic rock formations in East Asia suggests a more complicated arrangement. Some of those deposits preserve climate signals that align less closely with a continent dominated by one immense seasonal circulation. Alternative models, emphasizing broader east to west climate zones, explain portions of the record equally well. At present, neither interpretation accounts perfectly for every observation, encouraging scientists to refine both rather than declaring either complete. The timing of the Great Dying also continues to receive careful examination. Improved dating techniques have narrowed many uncertainties, yet important questions remain. Certain marine rock sequences indicate that the principal wave of extinction unfolded in fewer than 20,000 years, an interval astonishingly brief on geological timescales. Other locations preserve evidence suggesting multiple pulses of environmental crisis separated by much longer periods. Researchers continue comparing fossil distributions, volcanic deposits, and chemical signatures from around the world to determine precisely how ecosystems collapsed, which organisms disappeared first, and how different environmental stresses interacted through time. Another unresolved mystery centers upon Lystrosaurus. This sturdy synapsid became one of the defining animals of the early Triassic, thriving when countless other large terrestrial species vanished. Paleontologists have proposed several possible explanations. Burrowing behavior may have provided temporary refuge from harsh surface conditions. Periods of reduced metabolic activity could have conserved energy during environmental instability. A flexible diet may have allowed survival when preferred food sources disappeared. Chance itself also cannot be dismissed, since extinction sometimes removes closely related species while sparing others under seemingly similar circumstances. No single explanation has yet earned universal acceptance, leaving one of the most successful survivors of Earth's greatest biological crisis, surrounded by genuine scientific uncertainty. Debate also continues regarding the relationship between the formation of Pangea and the Great Dying. The Siberian Traps clearly released enormous quantities of volcanic gases capable of transforming climate and ocean chemistry. Yet the geography of the supercontinent may already have created vulnerable conditions before those eruptions reached their greatest intensity. Reduced shallow seas, altered circulation, and changing marine environments could have increased ecological stress. Determining how much influence belonged to continental arrangement and how much resulted from volcanism remains an active field of investigation. These unanswered questions represent the natural edge of scientific understanding. Every newly dated rock layer, every fossil discovered within previously unexplored sediments, and every improved analytical method has the potential to reshape familiar ideas. The story of Pangea, therefore, remains a living investigation, reminding us that the history of Earth is not only preserved within stone, but also continually rewritten through discovery. Movement on the scale of continents escapes ordinary perception. Mountains appear fixed, shorelines seem permanent, and familiar landscapes encourage the impression of stability. Modern instruments reveal another reality. Beneath cities, forests, deserts, and oceans, Earth's outer shell continues its gradual journey. The process that assembled and divided Pangea never ended. It remains active at this very moment, advancing with remarkable consistency across the surface of the planet. This conclusion rests upon direct measurement rather than inference. Networks of global positioning system satellites repeatedly determine the positions of carefully monitored locations around the world with extraordinary precision. Measurements accurate to fractions of an inch accumulate year after year, producing an uninterrupted record of continental motion. The observations are publicly available, continually updated, and independently confirmed by scientists across many nations. They leave no meaningful uncertainty that every major continental plate continues traveling along its own path. North America is steadily moving away from Europe at roughly 1 inch each year, about the same pace as human fingernails grow. That gradual separation widens the Atlantic Ocean little by little as fresh oceanic crust forms along the mid-Atlantic ridge. Far to the east, India continues pressing into Asia at approximately 1.7 inches per year. The immense pressure generated by that collision keeps lifting portions of the Himalayan mountains, reminding geologists that mountain building remains an ongoing process rather than an event confined to the distant past. Australia currently travels northward at nearly 2.8 inches each year, making it the fastest moving major continental plate on Earth. Its motion has become significant enough that mapping systems within Australia have required periodic adjustment to account for the continent's changing position. Africa also continues its gradual movement toward Europe at about 0.8 inches annually. Given enough geological time, this convergence is expected to eliminate the Mediterranean Sea as surrounding land rises into a new mountain belt where open water exists today. The oceans respond to these motions in different ways. The Atlantic continues expanding because new crust forms faster than old crust disappears along its margins. The Pacific follows the opposite pattern. Encircled by numerous subduction zones, its oceanic crust continually descends back into Earth's mantle. For at least 200 million years, since the decline of Panthalassa began, the Pacific Basin has gradually lost area, even while remaining the largest ocean on the planet. Every stage of this ongoing transformation leaves physical evidence. Fresh volcanic rock emerging along ocean ridges cools and records the direction of Earth's magnetic field at the moment it solidifies. As magnetic reversals occur through geological history, alternating bands become preserved across the seafloor like an expanding archive. Ice accumulating across Antarctica stores additional environmental records year after year, while volcanic rift valleys preserve new layers documenting continental separation as it unfolds. Millions of years from now, those records will remain embedded within rock and ice. Any future observer capable of reading magnetic patterns and comparing them with the established sequence of Earth's magnetic reversals could determine when each stretch of seafloor formed and calculate the speed at which continents traveled during our own lifetime. The world beneath our feet is writing that history continuously, one measured movement at a time. Earth's continents are travelers without a final destination. Their present arrangement is only one moment within a much longer cycle that has repeated across geological history. Earlier supercontinents assembled, endured, fragmented, and gave rise to new oceans before the process began again. Plate tectonics has never paused, which means the continents visible today will not remain separated forever. Another supercontinent will eventually emerge, although its appearance remains a matter of scientific debate. One of the earliest and most influential reconstructions is Pangea Proxima, also known as Pangea Ultima. American geologist Christopher Scotez introduced this concept in 1982 after examining long-term plate motions and possible changes in subduction. In this model, the Atlantic Ocean eventually stops expanding. Fresh subduction zones develop along its margins, drawing oceanic crust back into Earth's interior. As millions of years pass, North America and South America begin moving once more toward Europe and Africa. Continents that gradually separated after the age of Pangea eventually reunite in a configuration broadly resembling their ancient arrangement. This scenario places the assembly of the new supercontinent roughly 250 million years in the future. Another proposal envisions an entirely different outcome. Known as Novo Pangea, this model assumes that the Pacific Ocean continues following its present trend. Subduction zones surrounding the basin steadily consume its seafloor, while the Atlantic keeps widening. The Americas drift westward until they collide with Asia and Australia. Rather than recreating an earlier pattern, this version assembles a supercontinent on nearly the opposite side of the globe from where Pangea once existed. A third possibility is called Amasia. Computer simulations supporting this model suggest that several continents gradually migrate toward high northern latitudes instead of converging around the equator. North America eventually joins Asia near the Arctic region, while additional continental fragments gather nearby. The Arctic Ocean closes during the process, producing a polar supercontinent unlike any arrangement confirmed within Earth's known geological record. Research conducted by the Earth Dynamics Research Group at Curtin University has contributed significantly to this interpretation through advanced numerical modeling of plate motion. The most speculative proposal bears the name Orica. It imagines a future in which both the Atlantic and Pacific Oceans eventually close, while an entirely new ocean basin develops across Central Asia. Continental fragments then assemble around equatorial latitudes, creating a geography unlike either Pangea or the other predicted configurations. Although physically possible under certain assumptions, this model depends upon tectonic developments that remain especially difficult to evaluate with present knowledge. Each reconstruction follows the same fundamental laws governing plate tectonics. All rely upon observations of moving continents, subduction, mantle convection, and the creation of new oceanic crust. Their differences arise because one crucial question has no definitive answer. Scientists cannot yet determine with confidence where entirely new subduction zones will appear, or precisely how mantle circulation will evolve across hundreds of millions of years. Those unknowns influence every later stage of continental motion. The existence of another supercontinent is therefore regarded as highly probable, while its exact form remains beyond current prediction. Four carefully constructed models, developed from the same physical principles, produce four distinct future worlds. The uncertainty lies not in whether Earth's continents will gather again, but in the shape they will ultimately create when that distant chapter finally arrives. Across Earth's history, continents have gathered and separated often enough to reveal a repeating pattern rather than a collection of isolated events. Geologists describe this long sequence as the supercontinent cycle, a process woven into the behavior of the planet itself. It arises from the interaction between Earth's metallic core, its slowly circulating mantle, and the thin tectonic plates that carry oceans and continents across the surface. The cycle unfolds so gradually that no single generation could witness more than the smallest fraction, yet its effects shape every age of geological history. When continents gradually assemble into one enormous landmass, they influence more than geography. The combined continent acts as an insulating cover above portions of the mantle. Much of Earth's internal heat normally escapes through spreading centers beneath the oceans, where fresh crust forms along mid-ocean ridges. As those ridges become concentrated around the margins of a supercontinent, the transfer of heat changes. Energy continues rising from deep within the planet, while the broad continental mass slows its release across the covered mantle below. Over tens of millions of years, that retained heat contributes to changes within the underlying mantle. Hotter material becomes increasingly buoyant, encouraging upward movement that places stress upon the continental crust overhead. Fractures begin forming across regions weakened by earlier tectonic events. Those fractures widen into rift valleys, volcanic activity increases, and eventually new ocean basins appear between separating continental fragments. The supercontinent does not remain permanent because the very conditions created by its assembly gradually encourage its fragmentation. As separation continues, fresh oceanic crust develops between the drifting continents. Mid-ocean ridges lengthen, allowing internal heat to escape more efficiently once again. Ocean basins expand, circulation within the mantle adjusts, and tectonic forces continue redistributing the continents across the globe. After immense intervals, those wandering fragments encounter one another through subduction and collision. New mountain ranges rise, oceans disappear, and another supercontinent ultimately takes shape, beginning the sequence once more. Evidence suggests this cycle has continued for at least 2 billion years, encompassing nearly half of Earth's history. Geologists have reconstructed several ancient supercontinents from preserved rocks, magnetic signatures, and the alignment of long vanished mountain belts. Among the best supported are Kenorland, Nuna, Rodinia, and Pangea. Each existed during a different chapter of planetary history, separated by hundreds of millions of years. Earlier supercontinents may also have formed before these, although the oldest portions of Earth's crust have been repeatedly altered, buried, and recycled, leaving only fragmentary clues from those distant eras. The rhythm itself does not resemble the regular motion of a clock. Individual cycles appear to vary considerably, lasting somewhere between roughly 300 million and 600 million years, depending upon mantle, circulation, plate interactions, and the evolving structure of Earth's interior. Even with those variations, the recurring pattern remains recognizable throughout the geological record, supported by independent lines of evidence gathered from continents around the world. Today, Earth occupies the dispersal stage of that continuing cycle. The continents remain separated by broad oceans that continue evolving through plate motion measured year after year. Far below them, Mantle circulation persists without pause, gradually preparing conditions that future generations of continents will eventually inherit. The process has endured through immense stretches of time, carrying the planet through repeated transformations while maintaining the same enduring geological rhythm. The future supercontinent will not be a copy of Pangea. Its coastlines will differ, its mountains will rise in unfamiliar places, and the living world that inhabits it will bear little resemblance to the one known today. Even so, the underlying forces shaping that distant landscape will follow the same physical principles that governed every earlier cycle. Rocks, oceans, heat, and gravity will operate according to the same rules, regardless of which continents eventually unite. As continental fragments converge into a single immense landmass, climate will respond to that changing geography. Ocean winds carrying moisture inland will encounter increasing distances before reaching the continental center. Rainfall will become concentrated near many coastal regions, while interior environments grow progressively drier. Seasonal circulation across such an enormous landmass is expected to strengthen, producing atmospheric patterns comparable to the megamonsoon systems inferred for Pangea, even if their exact details differ. Temperature contrasts between coastal margins and inland regions will likely become more pronounced as maritime influence diminishes with distance. Marine ecosystems will also experience profound change. When separate continents merge, long coastlines disappear as ocean basins close and collisions reshape the edges of the land. Broad continental shelves, among the most productive marine habitats on Earth, become less extensive. At the same time, enclosed warm seas may develop where portions of the new supercontinent curve around remaining bodies of water. Those sheltered marine environments could resemble the ecological role once played by the Tethys, providing conditions that support diverse communities while surrounding regions undergo continuing transformation. Life would encounter selective pressures created by those changing landscapes. Species able to tolerate fluctuating climates, varied food supplies, and shifting habitats would likely possess important advantages. Organisms with specialized requirements could face greater challenges if familiar environments became less widespread. Evolution has repeatedly demonstrated that periods of environmental stress alter the balance among living communities, favoring lineages capable of adapting to unfamiliar circumstances. Which organisms eventually flourish cannot be predicted because that outcome depends entirely upon the descendants present when those distant changes begin. The Great Dying transformed Earth's biosphere through a unique combination of volcanic activity, environmental disruption, and biological loss. Lystrosaurus emerged as one of the defining survivors of that extraordinary interval, yet no physical law requires another future crisis to produce a comparable animal or even a similar pattern of evolution. The inhabitants of the next supercontinent will inherit whatever evolutionary history unfolds during the hundreds of millions of years leading to its formation. Every extinction, every adaptation, and every successful lineage between now and then will influence that future world in ways impossible to anticipate. This expectation rests upon observation rather than imagination. Geological evidence demonstrates that supercontinents have assembled repeatedly, each reshaping oceans, climates, and ecosystems according to consistent physical processes. Differences emerge because every cycle begins with a different arrangement of continents and a different collection of living organisms. The details change, while the governing mechanisms remain recognizable across immense spans of time. Whenever the next supercontinent finally appears, life will once again encounter a world reorganized by plate tectonics. Some lineages will adapt, others will disappear, and new evolutionary paths will emerge from those that endure. The geography will be unfamiliar, yet the planet itself will still be following the same enduring rhythm that has guided Earth through countless ages before. A map can appear to be nothing more than an arrangement of coastlines, mountains, and oceans. Viewed across geological time, it becomes something far more influential. The position of continents determines where species can travel, where they become isolated, and how evolution unfolds through countless generations. Geography does not choose which organisms survive, yet it shapes the possibilities available to every lineage. Across Earth's history, that influence has proven as profound as climate, inheritance, or competition. When continents remain connected, animals and plants can spread across immense territories with relatively few barriers. Successful adaptations expand into new regions, meeting similar competitors over enormous distances. Populations remain linked through continuing exchange, allowing genetic variation to move across broad landscapes instead of remaining confined to one place. Ecological communities become increasingly interconnected as similar environments support many of the same dominant forms. Evolution continues without pause, although it does so across one immense biological network rather than many separate ones. That connected arrangement also carries an important consequence during periods of environmental crisis. A severe disruption affecting the shared landmass can influence ecosystems almost everywhere at once. Opportunities for long-term isolation become fewer because populations remain linked through continuous habitats. If widespread environmental change overwhelms a successful lineage, distant populations may encounter the same conditions with little chance to remain untouched. The living world becomes remarkably integrated. Yet integration can also increase shared vulnerability when global pressures intensify. A fragmented planet creates different opportunities. Oceans separate populations that once exchanged genes freely, allowing evolution to proceed along independent paths. Similar ecological roles remain necessary on every continent, although different organisms may eventually occupy them through separate evolutionary histories. Comparable predators, grazers, climbers, or burrowers can arise from unrelated ancestors because each isolated landmass develops its own solutions to familiar environmental challenges. Diversity expands as these parallel histories continue over millions of years without frequent contact. Isolation also changes the outcome of extinction. A catastrophe capable of transforming one continent may leave another comparatively unaffected if oceans prevent the disturbance from spreading with equal intensity. Species disappearing from one region may continue surviving elsewhere, preserving evolutionary branches that otherwise would have vanished entirely. Those surviving populations later diversify again, enriching Earth's biological complexity through repeated episodes of separation, persistence, and adaptation. Geography becomes an unseen participant in evolution, influencing which histories continue and which conclude. Much of the extraordinary biodiversity visible across the modern world emerged within that fragmented setting. Millions of species, innumerable ecological relationships, and distinctive continental faunas developed after Pangea separated into independent landmasses. Natural selection remained the engine of evolutionary change, yet the opportunities upon which it acted were created by moving continents. Plate tectonics provided the stage upon which evolution explored many different possibilities simultaneously instead of repeating the same outcome across one continuous landscape. Looking backward reveals the opposite pattern during the closing chapter of the Permian. The eruption of the Siberian Traps occurred within a world whose continents remained united. Marine environments had already become less varied as coastlines merged, while terrestrial ecosystems stretched across immense connected regions. Few geographical barriers existed to preserve isolated biological refuges from escalating environmental stress. The remarkable integration that had allowed life to spread so widely also reduced opportunities for escape when conditions deteriorated. The history of Pangea, therefore, reveals an enduring partnership between geology and biology. Continents determined where life could travel, where it paused, and where it discovered new directions. As Earth reshaped its surface, evolution reshaped its inhabitants, each responding to the possibilities written into the changing geography of the planet. Stand upon any shoreline, mountain, or plain, and the landscape seems enduring beyond imagination. Human memory measures permanence in generations, civilizations, and written history. Earth measures it differently. Across geological time, every coastline migrates, every mountain changes, every ocean opens and closes. Features that appear timeless exist only for a chapter before the planet reshapes them into something entirely new. The Atlantic Ocean offers one of the clearest examples. Its waters stretch between continents with such familiarity that they seem inseparable from Earth itself. Yet the Atlantic began opening only about 180 million years ago as the fragments of Pangea drifted apart. Compared with the age of the universe, estimated at roughly 13 billion and 800 million years, the Atlantic is astonishingly young. On that immense scale, its history occupies only a brief interval, more comparable to adolescence than maturity within a much longer existence. Mountain ranges tell a similar story. The Himalayas dominate the horizon across much of Asia, their towering peaks suggesting immovable permanence. Their formation, however, belongs to a comparatively recent chapter of Earth's history. They began rising around 50 million years ago as the Indian continent continued pressing into Asia. That collision has never concluded. The rocks remain under compression, and portions of the range continue lifting today. Mountains, often regarded as symbols of geological endurance, are, by planetary standards, among the youngest great ranges still under active construction. The Mediterranean Sea also appears deeply rooted within human history. Along its shores flourished the Phoenicians, the Greeks, the Romans, the Ottomans, and countless other civilizations whose cultures shaped large portions of the modern world. Even this familiar body of water occupies only a temporary place upon the globe. Africa continues moving toward Europe, gradually narrowing the basin. If present tectonic trends continue across approximately 50 million years, the Mediterranean will disappear as continental collision raises new mountains where ships now cross open water. This pattern extends beneath every landscape inhabited today. The bedrock supporting cities, forests, deserts, and farmland has occupied many different settings through deep time. Rocks now standing high above sea level may once have rested beneath tropical oceans. Sediments buried beneath grasslands may preserve traces of coral reefs or coastal marshes. Regions presently covered by temperate forests have existed within scorching continental interiors, separated from rainfall by immense distances. Every location carries a history far older and more varied than its present appearance suggests. Geological maps therefore resemble individual frames taken from an unimaginably long motion picture. The arrangement of continents and oceans visible today represents one instant within a story that began about 4 billion and 500 million years ago. Earlier frames displayed worlds unlike our own, while future ones will reveal coastlines, mountains, and seas that no human has ever witnessed. Each configuration follows naturally from the one before it, connected through the continuous motion of Earth's tectonic plates. Pangea belonged to one chapter of that unfolding narrative. The modern world belongs to another. Neither represents a permanent destination nor a final design. Continents continue their gradual journeys. Oceans continue evolving, and mountains continue rising and wearing away. Beneath every familiar horizon, the same restless planet carries forward a history that has never stopped changing and shows no sign of ever becoming still. The connection between the present world and Pangea reaches deeper than fossils, continents, or the shared ancestry of living creatures. It exists at the level of matter itself. Every atom follows journeys far longer than the lifespan of any species, passing from air to water, from rock to living tissue, then returning again. The landscapes of the distant past have vanished, yet the material that composed them continues circulating through Earth's enduring cycles. Forests that covered portions of Pangea drew carbon dioxide from the atmosphere through photosynthesis, building trunks, branches, roots, and leaves from carbon that had drifted through ancient air. When many of those forests died, some became buried beneath sediments before complete decay could occur. Pressure and heat gradually transformed that organic material into coal across immense spans of geological time. During the modern age, much of that coal has been mined and burned, returning its carbon dioxide to the atmosphere. Some of the carbon floating through today's skies therefore once formed the living tissues of plants rooted upon a supercontinent that disappeared long ago. Those same atoms followed many other paths before returning to the air. Carbon passed through the lungs of gorgonopsids wandering across Permian landscapes. It entered the bodies of marine organisms living within the warm waters of the Tethys Sea. It became part of soils carried by seasonal floods and winds across broad continental interiors. None of those individual organisms survived, yet the atoms themselves continued moving from one form to another, never leaving the planet that continually recycled them. Stone preserves another chapter of that continuity. Large deposits of limestone found across parts of the Middle East originated within ancient marine environments where countless shell-bearing animals and reef-building organisms extracted dissolved calcium from seawater. Their skeletons accumulated upon the seafloor, layer after layer, before becoming compressed into solid rock. Across hundreds of millions of years, tectonic uplift raised portions of those former seabeds above sea level. Quarries later supplied stone for towns, monuments, and modern buildings. Walls standing in contemporary cities may therefore consist of rock that once formed the framework of thriving marine ecosystems within the Tethys. The elements composing our own bodies have followed equally remarkable histories. Iron circulating through human blood was forged inside stars that existed long before Earth formed. That iron later became part of the rocks composing mountains across Pangea before weathering, erosion, and countless chemical processes redistributed it through soils, rivers, oceans, and living organisms. Calcium, now supporting human bones, also completed repeated journeys through seawater, shells, limestone, sediments, uplifted rock, and dissolved minerals before becoming available once again to living creatures. These transformations never destroy matter, they rearrange it. Atoms move between the atmosphere, oceans, continents, and the biosphere through cycles that continue without interruption. A grain of limestone may someday dissolve into seawater. Carbon released into the atmosphere may become part of a future forest. Iron within blood may eventually return to stone through entirely different pathways. Every transition preserves the same fundamental material while changing its role within Earth's systems. Pangea itself has vanished as a geographical arrangement, yet its substance remains present everywhere. The rocks, waters, gases, and living bodies of today contain matter that participated in worlds separated from us by hundreds of millions of years. Nothing belonging to that ancient continent truly disappeared. It has continued its patient journey through Earth, arriving in new forms while remaining composed of the same enduring atoms. Every passing day leaves a trace within the planet. Most vanish from human memory almost immediately, yet Earth preserves them with remarkable patience. Tiny grains settle across the seafloor. Minerals crystallize inside cooling lava. Snow falls upon polar ice, capturing a thin sample of the atmosphere before another season buries it. The archive that revealed Pangea to modern science has never closed. It continues expanding with every passing year, recording the present as faithfully as it preserved the distant past. Across many ocean basins, fine layers of sediment accumulate one upon another. In some places, a distinct layer forms every year, preserving microscopic shells, grains of dust, volcanic ash, organic material, and chemical signals carried through seawater. Together, they create an uninterrupted history of changing climates, shifting ecosystems, and atmospheric conditions. Millions of years from now, a future researcher recovering one of these sediment cores could recognize this interval just as modern geologists identify ancient turning points preserved within older rocks. Every layer belongs to a precise moment that once existed at the surface of a living planet. Elsewhere, Earth's crust continues forming where tectonic plates separate. Molten rock rises from the mantle, cools beneath the oceans, and locks into place. As minerals crystallize, they align with the direction of Earth's magnetic field existing at that exact time. The magnetic pattern becomes fixed within the newly formed crust, creating another enduring record. Long after today's continents have shifted into unfamiliar positions, those rocks will still preserve the orientation of the magnetic field present during their formation, allowing future investigators to calculate when that crust emerged and how tectonic plates moved across the globe. The frozen landscapes of Antarctica preserve another chapter of this continuing archive. Year after year, fresh snowfall compresses older layers into solid ice, trapping tiny bubbles of ancient air within the growing ice sheet. Those bubbles preserve samples of Earth's atmosphere from the moment each layer formed. Ice cores recovered by scientific expeditions already extend back nearly 1 million years, revealing changes in temperature, greenhouse gases, volcanic eruptions, and seasonal cycles. Each new drilling campaign lengthens that remarkable record, adding greater detail to the history preserved beneath the polar surface. The evidence accumulating today will remain available far beyond the span of human civilization. Future investigators, whatever form they may take, could examine rock layers from this age and identify distinctive signatures preserved within them. They may recognize changes in atmospheric carbon dioxide, magnetic patterns frozen into oceanic crust, pollen preserved in sediments, or fossils representing the organisms that inhabited our world. Those discoveries would allow them to reconstruct this chapter with methods resembling the ones scientists use to understand Pangea. In that sense, the study of Earth's history reaches in both directions through time. We recover stories recorded by vanished landscapes while adding new pages to the same enduring archive. Every continent, every ocean basin, every glacier, and every volcanic ridge contributes another line to that record without interruption. Pangea therefore belongs to a narrative that remains unfinished. Continents assembled before it, continents separated after it, and continents will gather again long after the present arrangement has passed into history. We occupy one brief interval within that continuing story, reading the pages left behind while the planet patiently writes another beneath our feet.